Hello one and all, welcome to another online video by Einstein Academy. In the last video, we looked at learning outcomes D and E from the topic of chemical bonding from the JCH2 chemistry syllabus. In this video, we will look at a few A-level questions that specifically test on these two learning outcomes. So these are learning outcomes D and E. I'm not going to read through them again. However, I'd just like to summarize these two learning outcomes by saying that in these learning outcomes, you need to be able to use the VS-EPR theory to basically predict both the shape and the bond angles in many different covalent molecules. Okay, so question November 2009, paper 1, question 19. Predict the most likely bond angle at each nitrogen atom in diimine. So nitrogen is in group 5. So if you were to look at the number of electron domains around this nitrogen atom, it would actually be such. Okay, so like this. Okay, and if you look at the number of electron domains around this central nitrogen atom, it's actually a total of 3 electron domains, 1 electron domain, 2 electron domains, and 3 electron domains for basic geometry of trigonal planar, which is supposed to be 120 degrees. However, because of the stronger lone pair bond pair repulsion, it will actually cause this bond angle to be compressed to be smaller than 120 degrees so that it minimizes the lone pair bond pair repulsion, and therefore the bond angle would be on the order of about 118 degrees. So again, I repeat the process to figure out the shape and bond angle. Number one, figure out the number of electron domains around a certain atom to determine the basic geometry, then replace the electron domains with the lone pair, making them invisible to the overall shape around that central atom, and then basically compress the bond angles accordingly due to the fact that the lone pair bond pair repulsion is stronger than the bond pair repulsions. Okay, November 2010, paper 1, question 5. What value of the bond angles in the pH3 molecule would the VS-EPR theory predict? So phosphorus is in group 5. So there is actually 4 electron domains around this phosphorus atom. Okay, giving a basic shape of tetrahedral. However, one of them is invisible to the overall shape of the molecule. So the shape of this molecule is trigonal, pyramidal. Trigonal because there are actually 3 groups around the phosphorus, and then it's in a pyramidal shape. Okay, so the bond angle should be 109.5, but again, it's compressed by the lone pair bond pair repulsion. So it'll be smaller than 109.5 degrees. So it will be on the order of about 107 degrees, option B. November 2014, paper 1, question 5. The VS-EPR theory is used to predict the shapes of molecule. Which shape is correctly predicted by VS-EPR? Okay, so if you look at all 4 options, there's actually 4 electron domains around the central atom, 2 plus 2, 2 plus 2, 3 plus 1, 3 plus 1. Okay, so if you have a 4 electron domain around a central atom, so the central atom, I'll call it A. Okay, so the basic shape would be of the form of a tetrahedral shape. If 2 of them are actually lone pairs, so like we replace 2 of them and make them invisible to the overall shape of the molecule. So the overall shape of the molecule is just DAE, in which it will be a bend shape. If we were to look at the bond angle, it will be much smaller than 109.5 degrees, which will be about approximately 105 degrees. Okay, so this is actually a bend shape. But if you look at option A and B, none of them is actually bent. We can definitely rule out option B because it's definitely not a tetrahedral shape. However, nonlinear is also another way of saying bent, right? Because nonlinear just means not straight. We would like to come back to this option to see whether is it the best possible answer. If we look at option C, out of the 4 electron domains, one of them is a lone pair, which means that when we replace one of them as a lone pair of electrons, we will arrive at this overall shape. And this shape is called a trigonal pyramidal shape, as mentioned in the other questions. Trigonal because there's 3 groups and it's in a pyramidal shape. It's definitely not trigonal planar in option C, and it's also definitely not linear in option D. Hence, A is the best possible answer, and we will have to accept that the shape is called nonlinear instead of it being bent. In MCQ, you just always choose the best possible answer. November 2015, paper 1, question 5. What bond angle is present in the molecule of aminoethanoic acid? This, but it's not present in Zwitter ion. So I understand that you have not learned Zwitter ion. This is covered properly in the topic of organic chemistry, but I'll just quickly go through them for the purpose of this question. Okay, so let's look at the H2NCH2CH2 molecule, COOH molecule first. So if we were to draw the molecule out, it would roughly look like this. Okay, I'm just going to draw a 2D view, right? This is not the actual 3D view. So there's a lone pair of electrons on nitrogen because it's in group 5. And then you have this shape, CH2, and then you have COOH. So let's look at some possible bond angles. So the number of electron domains around this nitrogen is 4. 1, 2, 3, 4 for a basic shape of tetrahedral. So this bond angle should be about 109.5 degrees. However, it's being compressed by the lone pair bond pair repulsion. So this bond angle would be on the order of 107 degrees. The number of electron domains around this carbon is 4. And there are actually no lone pairs around this carbon atom. And therefore, the shape around this carbon will be a tetrahedral shape. And this bond angle will be 109.5 degrees. For this part of the molecule, there are 3 electron domains around this central carbon atom, and hence it will be 120 degrees because the basic geometry will be in the form of a trigonal planar arrangement. Okay, if you look at this molecule, the zwitter ion, this molecule has a COOH group, which is a carboxylic acid group, and it also has an NH2 group, which is actually an amine group that is basic. So what it means is that it can undergo internal self-neutralization, whereby the COOH donates a H+, and the H+ is accepted by this amine group by the nitrogen on this amine group. And in the process, it will actually form this zwitter ion. Okay, the zwitter ion, there will be a plus charge on this nitrogen, and there will be a negative charge on this carboxylate ion group. Okay, that's why it's called a zwitter ion. Zwitter ion means like dual ion. Okay, there's a plus and a minus group. Now, this bond angle, the number of electron domains around this nitrogen is still 4, but however, there is now no lone pairs of electrons, so the bond angle will not be compressed, and the bond angle will be exactly 109.5 degrees. And this will again still be 109.5 degrees, no change. And this will also be no change at 120 degrees because the number of electron domains is still 3 and there is no lone pair of electrons. So if you were to compare between this molecule and this molecule, the 109.5 degrees is present in both. The 90 degrees is not even present in any 2 molecules. So as in option A is wrong. 109.5 degrees is actually present in both this molecule and the zwitter ion. So option C is also wrong. The 120 degrees is also present in both molecules. So D is also wrong. However, the 107 is only present in the non-zwitter ion, while it's not present in the zwitter ion, and hence option B is the correct answer to this question. November 2011, paper 2, question 2b. Okay, phosphorus 5 chloride dissolves in some polar solvents without reaction, and some solutions conduct electricity. This is due to the presence of the 2 ions PCl4 plus and PCl6 minus. Draw the structure and suggest the shape of each of these ions. Okay, so phosphorus is in group 5, and since it's positively charged, we can remove 1 electron, and hence there is 4 electrons remaining in the valence shell. Chlorine is in group 7, hence it needs to form 1 covalent bond. Hence, the bonding between the phosphorus will be like this, whereby there is 4 electron domains around the PCl4 plus cation, and the shape of this will be a tetrahedral shape. Okay, because there are no lone pairs of electrons around the phosphorus. And although they only say that to suggest the shape of these ions, but my recommendation is also to add in the bond angle. So the bond angle will be equals to 109.5 degrees, which is representative of that in a tetrahedral shape. On the other hand, PCl6 minus, the phosphorus is in group 5, so it gains an electron. So we can say that there's 6 electrons in the valence shell, and it will form single bonds with each of the 6 chlorine atom, and there'll be 6 electron domains around the phosphorus, and the shape of the molecule for PCl6 minus will look like this, whereby there are 6 electron domains around it, and this shape, it's known as the octahedral shape. And if you were to quote the bond angles, there will be a few bond angles that we can quote. There will be a bond angle of 90 degrees, and there will also be bond angle of 180 degrees. So that's the answer to this question. November 2010, paper 3, question 4. Draw dot and cross diagrams to show the bonding in the molecules of NO2 and O3. Okay, so they also tell you that each molecule contains a dative covalent bond, and the NO2 molecule, the central atom is nitrogen. In each case, you should distinguish carefully between electrons originating from the central atom and those from the 2 outermost atoms. and to include all lone pairs in your diagrams. So if we look at the NO2 molecule, the nitrogen is the central atom. It has 5 electrons, and it will be using a dative covalent bond to form a dative covalent bond with this oxygen. Okay, so this is a single dative covalent bond between nitrogen and oxygen, while the other one will be a double bond, a normal covalent double bond. Okay, oxygen has 6 electrons in the outer shell. So this is basically a dot and cross diagram of NO2, but not forgetting that nitrogen is in group 5. So it has a single electron here. So the molecule of NO2 is a case whereby nitrogen doesn't have full noble gas octet configuration. Okay, so this is actually a very unstable molecule. In fact, actually dimerizes to form N2O4. I'll not talk more about that. Okay, so basically this is the dot and cross diagram of the NO2 molecule. For the ozone molecule, again ozone, the central oxygen atom will use one of its lone pair of electrons to form a dative covalent bond with the neighboring oxygen atom, while the other bond will be a normal double covalent bond. However, because oxygen is in group 6, so it will have a full lone pair of electrons. So both shapes will be bent. However, if we were to look at the bond angles of this molecule, right, because the repulsion between this electron and this is not as strong as this lone pair of electrons, because this one there are 2 electrons and this one is only a single electron. So it's not really a lone pair of electron, but it's a lone electron. But it's still true that the lone electron versus the bond pair of electrons, the repulsion is stronger. So it will cause a compression of this bond angle. So this bond angle by right should be 120, so it can be said to be compressed to be about 119 degrees. But this one, since the repulsion between the 2 electrons in the lone pair and the bond pair is stronger, it will cause a greater compression, and hence the bond angle of this can be said to be about 118 degrees. I hope it's clear why the repulsion of this is stronger and it causes a larger compression as compared to a weaker repulsion which causes a smaller compression, and hence this bond angle will be larger. Okay, so the second part is to suggest a value for the bond angle of each of the above 2 molecules, giving the reasons for your choice. So I already mentioned the reason as well as to suggest the value for the bond angle. In part C of the question, the compound FO2 does not exist, but ClO2 does. Okay, so by considering the possible types of bonding in the 2 compounds, suggest reasons for this difference. Assume that the halogen atom occupies a central position in each of these molecules. So let's first look at the ClO2 molecule. So if you look at the ClO2 molecule, chlorine actually has 7 electrons and needs to bond with 2 oxygens. So an oxygen needs to form 2 covalent bonds to achieve noble gas configuration. So we can say that chlorine will form a double bond with an oxygen and another double bond with an oxygen, and it will be using 4 electrons in these bonds, and therefore it will still have 3 remaining electrons, and hence it will have 3 remaining electrons. So the shape of ClO2 will be as such, whereby this is a lone pair and this is a lone pair, and you will have this for a band shape. Okay, and the thing is that if you count the number of electrons around this chlorine atom, right, you would see that, right, it actually has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons in the outer shell. However, this actually violates the octet rule, right? Because like we say that most atoms will want to achieve a stable noble gas configuration, which is usually 8 electrons in the outer shell. However, this violates the octet configuration. However, it's okay for chlorine to violate the octet rule. The reason is because chlorine is in period 3 and it can expand its octet by using the energetically accessible d orbitals for bonding, and therefore ClO2 exists. However, if we were to let FO2 form this bonding, right, the same thing will actually apply. The shape will be exactly the same. However, it will still have 11 electrons in the outer shell. However, it's not allowed for fluorine to have 11 electrons in the outer shell because of the fact that fluorine is in period 2 and you cannot expand the octet. Okay, because the d orbitals are not energetically accessible for period 2 elements to form extra bonding. that is above that of 8 electrons in the outer shell. So this molecule doesn't exist because fluorine is in period 2 and is unable to expand the octet, while this molecule exists because chlorine is in period 3 and is able to expand octet, and hence is allowed to have more than 8 electrons in the outer shell of the molecule. November 2011, paper 3, question 1b. Draw dot and cross diagram showing the electrons in ClF5 and ICl4- and use the VSEPR theory to predict their shapes. Okay, you may find both a written description and a 3-dimensional sketch useful in your answer. So let's look at the ClF5 first. So ClF5 has 7 valence electrons, 5 of which will be used for bonding with the fluorine, and there will be 1 lone pair of electrons. So there will be 6 electron domains around ClF5. So the case of 6 electron domains is whereby we put a lone pair in the equatorial region, and then one of this will be the fluorine. Okay, and this will be a fluorine, and this will be a fluorine. Okay, anyway, like, I understand that I didn't really draw a dot and cross diagram, but if you were to put in a dot and cross diagram, it would just replace it with like this. And then like fluorine will be like this. Okay, but anyway, the shape of this is a seesaw shape. Okay, now ICl4-, so iodine is in group 7, it gains an electron, so we can see that there's 8 electrons in the outer shell, 4 of which will be forming single covalent bonds with chlorine, which means that there will be 2 lone pairs of electrons, which means that again there will be 6 electron domains, out of which 2 are lone pairs. So 6 electron, let me see, 1, 2, 3, 4, 5, 6 electron domains is octahedral shape, the basic geometry of octahedral shape, out of which 2 are lone pairs. And we will put the lone pairs like opposite 180 degrees away from one another. And this will be chlorine, 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 and chlorine. Okay, so if you were to include all the electrons, it will look like this. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so that's correct. Just double checking my answer. Okay, so this will be a dot and cross diagram, and the shape of this molecule will be square planar. Okay, it's a square and it's flat, so it's a square planar molecule. Okay, November 2012, paper 3, question 1b, part 1 and part 2. So the following equilibrium exists in a sample of aluminum chloride vapor. So basically AlCl3, because it's a covalent compound, so the aluminum actually doesn't have an octet configuration. In fact, it's actually 2 electrons short of octet configuration. Hence, it actually undergoes dimerization in order to form the Al2Cl6 molecule by forming dative covalent bonds. Okay, so draw a dot and cross diagram of the Al2Cl6 molecule. So the AlCl6 molecule, I'm just going to draw this because it's an easy representation. I'm sure that you all can easily convert this into the dot and cross diagram. Okay, so like this, it's 2 AlCl3 molecules, and one of this is a dative covalent bond. Okay, suggest the shape of the AlCl3 molecule. So the AlCl3 molecule, the AlCl3 molecule looks like this. Okay, whereby there are 3 electron domains around the central aluminum atom, and there's no lone pairs, so it will actually be a trigonal planar arrangement. Trigonal because there's 3 groups, and it's a flat molecule, so it's trigonal planar molecule. And the bond angle will be equals to 120 degrees. Okay, so that's the answer to that question. Okay, so in this video, we look at a few past year A-level questions that specifically test on these 2 learning outcomes, which is basically to apply the VSEPR theory to decide on the geometry and the shape and the bond angle of every single molecule. I hope that now you have a clearer view of how to apply the principles of the VSEPR theory that you learned in the previous lecture. And if you have any questions, as before, just drop it down in the comments. I'll look at them and answer them maybe in a future video. And if you like this video, just hit the like and subscribe button. And I'll see you for another episode whereby we look at the next few learning outcomes from the topic of chemical bonding from the JCH2 chemistry syllabus. Thanks for tuning in, and bye-bye. See you.